The metric mishap. NASA's $327 million math error estimated the silence at JPL. Imagine the scene at the Jet Propulsion Laboratory on September 23, 1999. After a 286-day journey across the cold vacuum of space, the Mars Climate Orbiter was finally ready to tuck into its parking spot around the red planet. Engineers sat huddled around monitors, waiting for the signal that the probe had successfully completed its orbital insertion burn. The spacecraft dipped behind the far side of Mars, a standard blackout period where radio contact is expected to drop. But when the time came for the orbiter to emerge and say hello from the other side, there was only static. Minutes turned into hours, and hours into a grim realization: the $193 million spacecraft, and its $134 million in mission costs, was gone. It hadn't just missed its orbit, it had likely been incinerated in the Martian atmosphere or sent tumbling into a useless orbit around the Sun. The culprit wasn't a solar flare, a faulty engine, or an alien intervention. It was something far more mundane, and arguably more embarrassing: a failure to communicate in the same mathematical language. The mission and the faster, better, cheaper era. To understand how such a massive blunder occurred, we have to look at the culture of NASA in the late 90s. This was the era of faster, better, cheaper, a philosophy championed by then Administrator Daniel Goldin. The goal was to do more with less, to send more probes to more places on a fraction of the Apollo-era budgets. The Mars Climate Orbiter was a key piece of this puzzle, designed to act as a weather satellite and a communications relay for future landers. It was a lean, mean, scientific machine, built by Lockheed Martin Astronautics in Colorado and operated by NASA's Jet Propulsion Laboratory in California. For 9 months, the journey seemed flawless. However, beneath the surface, a tiny discrepancy was growing. Every time the spacecraft fired its small thrusters to maintain its orientation, a piece of software tracked the impulse the force applied over time. This data was crucial for the ground crew to calculate the spacecraft's exact trajectory. The language barrier, Newton seconds versus pound seconds. Here is where the $327 million disaster took root. At NASA, and throughout the global scientific community, the standard is the International System of Units, SI, commonly known as the metric system. However, the engineering team at Lockheed Martin had provided the small forces software using the English Imperial system. Specifically, the Lockheed software calculated the thruster impulse in pound force seconds, lbf middle.s. When this data was sent to the navigation team at JPL, the NASA computers assumed the numbers were in Newton seconds, n middle.s. The math is simple, but the consequences were catastrophic. 1 pound force is approximately equal to 4.45 newtons. This means that every time the thrusters fired, the ground crew was underestimating the effect on the spacecraft's momentum by a factor of more than 4. Over the course of a 416 million mile journey, these tiny, uncorrected errors compounded. By the time the orbiter reached Mars, it was significantly off course. The navigation team thought they were entering the atmosphere at a safe altitude of about 140 to 150 kilometers. In reality, the probe was diving as low as 57 kilometers. At that altitude, the thin Martian air is thick enough to act like a brick wall at orbital speeds. Why didn't anyone notice? The most taunting part of the Mars Climate Orbiter story is that the error was noticed, sort of. In the months leading up to the encounter, several navigators flagged that the spacecraft's position seemed to be drifting slightly off the predicted path. They even requested a manual check of the data. However, due to the faster, better, cheaper pressure, the mission was understaffed, and the communication channels between the ground crews were cluttered. The formal process to investigate these minor discrepancies was never fully triggered because the errors were small enough to be dismissed as noise or expected deviations. It was a classic case of cognitive bias. The team wanted the mission to succeed so badly that they overlooked the red flags. The investigation board later concluded that while the unit error was the technical cause, the root cause was a systemic failure in communication and a lack of rigorous independent checks. The legacy of a very expensive typo, the loss of the Mars Climate Orbiter, was a wake-up call that echoed through the halls of aerospace engineering. It led to a total overhaul of how NASA handles project management and cross-team communication. Today, the Mars unit error is taught in engineering schools worldwide as the ultimate cautionary tale. It's a reminder that in the world of high-stakes science, there is no such thing as a small detail. Since 1999, NASA has strictly enforced metric standards across all contractors and internal teams, ensuring that everyone is literally on the same page. We lost a $327 million probe, but we gained a priceless lesson. When you're shooting for the stars, you'd better make sure your ruler is the same as your neighbor's. It was a mistake that proved, quite literally, that the difference between success and a fireball in the Martian sky is often just a matter of basic arithmetic.